Okay, so the second point that we are having is effect of ligands, or if I'll say the spin states on delta. Generally, when we talk about the coordination complexes, they are mostly classified into two categories. One is low spin, and the other one is high spin. So this you are aware of. What is low spin and high spin? Low spin means mostly it would be having pairing of the d electrons, and that happens in presence of very strong pi acceptor ligands. Mostly in cases, it would be pi acceptor ligands that would cause the pairing of your d electrons. And here in high spin, there would be pi donors or sigma donor ligands. So here the donation is happening from the ligand to the metal, and in low spin case, metal is getting because some pi acceptors are there, so the electron density is getting reduced on the metal because of the pi acceptors are over there. So this is clear for you. Low spin and high spin. Generally, pi acceptor is like if you have nitro group or if you have this nitrile group, they will take up, because of the electronegativity, they will take up the electron density from the metal, which will make the d electrons to be either less or having pairing. Whereas in case of high spin, if you have some donor ligand, say for example, if I am having H2, which can be the electrons or more electron density is going there, and if I'm taking NMe3 or NH2 or something like that. So they become in pi donors or sigma donors. Now, in case of the low spin, why do we say low spin? Low spin is like mostly the electrons would be paired. Say, for example, if I have 3d6, it's a general case. It could be in high spin also, it could be in low spin also. So we know that in octahedral, if I have no splitting, so all the d orbitals would be like this way. This is d orbitals, and they are not splitting. But in presence of a ligand field, you would be having Eg and T2G orbitals. Here it would be having dxy, dyz, dzx. Here it is dx square minus y square, dz square. So I guess that you are well aware of what are the d orbitals. It goes from this +2, this is having +1, this is -2, sorry. So any values, if you will just take that going from +2, +1, 0, -1, -2, right? So this happens when ligand is coming into picture. That's why we are talking about the low spin and high spin depending upon the ligand. So if I have D6, 3d6, and 3d6 in case of high spin means most of the electrons would be unpaired over here. So if I have to fill in this manner, T2G and EG. So firstly, each orbital would be filled by one electron, that is filled, and the sixth electron would be coming as a pairing. So there are 4 unpaired electrons now. That is in case of high spin. If I have to draw the 3d6 in case of low spin, in low spin, as I said, pairing happens because of the electron density has been taken up from the ligands because they are accepting in nature. So firstly, 1, 1, 1 in each, and pairing also happens here only. It does not let the electrons to go to the excited state because of that pi accepting nature. So here you see all are paired, so there are no unpaired electrons. That's why there is no net spin. Spin is 0 right now because one upspin, downspin, upspin, downspin, the spin value becomes 0. That's why it is called as low spin. Whereas here there are 4 upspins, so that is called as high spin. Is this concept clear?
Clear, ma'am.
Okay. So now earlier we saw the oxidation state parameter. What if I have both iron in +2, but different spin states? One is in high spin, one is in low spin. Say, take the case of iron H2O whole 6, 2 positive, and iron CN whole 6, 4 positive. Here H2O, you know that this ligand is having no charge, so X plus 0 equals to 2. Here R is in plus 2 state, and here X Cn is having 1 minus charge, so it would be minus 6 equals to plus 4. This is sorry, minus 4. And when X goes there, it becomes positive. So it is plus 2. So both are in plus 2 only. But if you will see here, it's water ligand and here it is cyanide ligand. So water compared to water and cyanide, this one is pi accepting and this is donor. So if it is donor, it will make high spin complex, it will make low spin complex. So iron in H2O whole 6, 2 positive, iron Cn whole 6, 2 positive. Here we have kept oxidation state 4 negative. Oxidation state is constant. Iron in plus 2, iron in plus 2. Water is weak ligand. Cn is a very strong ligand. All the acceptor and donor acceptor ligands are very strong ligands. When strong ligand is there, pairing happens. So when a water is weak ligand, it will make it high spin and this will make it low spin. Now, iron 2 plus D6, it's high spin. The configuration would be 1, 2, 3, 4, 5, and 6. This is T2G5, 4, Eg2. Whereas in low spin, it would be pairing 1, 2, 3, 4, 5, 6. So it's T2G6, Eg0. Okay, you understand this now?
Clear, ma'am. Understood.
Now, the main factor that we were talking about, so we understood that how it is working. So in case of high spin complexes, we have metal d orbitals. So I'm making the orbital over here. We know that orbitals are having these volts, and here the ligand orbitals. So if I have a high spin case, high spin means if I have weak ligands and they have the donor properties. That means they are donating electrons to the metal. That means if d electrons are there, we are getting more electron strength to the d. So if it is more strengthened, that will cause more shielding, because as I said, ultimately we need to see more number of d electrons. So if more strength of d electrons are there, that will cause more shielding to your s electrons. When more d electrons are there, the s electron density would be less. That would be less, and therefore delta value become less negative. Is this clear?
Once again, explain in more strength, more shielding.
Okay. So, say for example, if I have here, this is a glass. So its capacity is okay, it can fill up to this much water. And now I am adding more to it. So I am a donor. I'm adding more to it. So this glass, I'm just giving a hypothetical example. So this glass would be having more water than. You can understand this effect?
Understand, ma'am?
Okay. Now, if I have the same glass with same water, but now I'm drinking it. So I am accepting the thing. I'm taking it from here. So it would be having now less water. Right?
Right, ma'am. Okay, ma'am.
Similarly, Now consider this as d electrons in metal, and this is a donor ligand. When it is giving, or weak ligands are called as donor ligands. If it is giving, then it would be having more strength of d electrons, right? Here the same d electrons, but now here the strong or accepting ligands, they are taking the d electrons from it, so that would be having less d electrons. Now you understood?
Understood, ma'am.
So we already seen the first concept, more oxidation state of the metal. When oxidation state is more, less d electrons. This is clear?
Clear, ma'am.
Yeah. So when less d electrons, it would be having less shielding effect on s electrons. That means this value s psi square would be less. If this is less, delta value is less negative. Sorry, this is opposite. If the shielding effect is less, the s electron density becomes more. So therefore, it would be more negative. That we saw now earlier in case of iron in +2 and +3. +3 was in more negative side, more left side. That is clear?
Clear, ma'am.
Okay. Now I'm not talking about the oxidation state, but I'm still talking about the d electrons. So in case of the spin state, now if I have low spin, that means more acceptor ligands, that would give me less d electrons, and therefore same concept, psi square would be more, there it would be more negative. Clear? Low spin means it would be having more accepting ligands, that is, they are going to take water from their glass. That means less d electrons, and when less d electrons, more less shielding effect, more s value. More s value means more delta negative. So the two factors that we combine here, just a second. Okay. So now we are combining both two factors. Firstly, higher oxidation state, when all the parameters are constant, that is going to have more delta negative. And if low spin complexes are there, that is also going to have more delta negative. So this is the effect on isomeric shift. Is this clear now? Any doubt? Because we should not move ahead until unless you understand the isomeric shift concept, because on this basis only other concepts would be clear, and we would be able to see directly the examples from different complexes. So is this clear? Like if the other parameters are constant, higher oxidation means less number of d electrons. When we have just one single concept for both the things, less number of d electrons, that would give you more isomeric shift in a negative direction. That means more negative delta value. Is this clear now?
Clear, ma'am.
Okay. Now we will move to more important factor. Okay, I'll just once again, I'll show you one more picture over here I have. Okay, so if you will see here now. Now see, here, just see the oxidation state first. We said higher oxidation state, more negative delta, that means more towards left side. Okay, and if low spin is there, that is also more towards left side. Just first see the same oxidation state. This is iron in +1, this is iron in +1, right? Iron in +1, iron in +1, same oxidation state, but look at their spin value. S equals to 3/2, 1/2. Which one is high spin, which one is low spin? Please try, even if you're wrong, that is fine. We are learning here. So what is low spin? Low spin means there is less number of unpaired electrons. The spin value is less. Which one is having less spin value? S1/2 is less or S3/2 is less?
1/2, ma'am.
Yeah. So when this is less, it becomes low spin. It becomes high spin. This is clear?
Clear, ma'am.
Okay. Now look at that. We said when low spin is there, if oxidation state is constant, if low spin is there, that is going to be more negative delta. That means more towards left side relative to the other. Now see which one is towards left side. S equals to half or S equals to 3/2?
S equal to 1/2, ma'am.
Yeah. Now this concept is clear that when we have both the metals in same oxidation state, then we look at their spin state. If one is low spin, that will go towards left side compared to the 3/2. Now take two different oxidation states, but having same spin value. Say for example, I have iron equals to this 3/2. This iron equals to 3/2 and iron equals to S equals to 3/2. Iron in +1 and iron in iron in +3, iron in +1. Both are 3/2, 3/2. So both are high spin only. So spin is constant. Now oxidation state is changed. Which one is going to have more negative, more delta value negative and more towards left side?
More oxidation state goes to negative side.
So you can see from here also, iron in +3, S3/2 is more towards left side compared to the iron in +1, S equals to 3/2. So this way only, when we know or the concept is clear that we are only looking for less d electrons, that will give you more delta negative. That concept validates for both spin states as well as the oxidation state. But we need to remember this in mind that when we are looking at one factor, say for example, oxidation state, the spin value has to be constant. You cannot have oxidation state is also different, spin state is also different. For example, here, if I'll start comparing iron +1, S equals to half, iron in +2, S equals to 2. So both the parameters are different. So it would be very difficult to compare these two. So let's just see that iron in +1. So let's see, we are taking iron in +1, iron in +2, S equals to half, S equals to 2. Now it's +1. We know that it is D7. This is D6, right? Looking at its spin state, it looks like it is low spin and it comes to be like high spin. It is that way. Now more electron density, more d electrons are there. It would give you more negative side compared to here. That would be less delta negative. So that is only happening, I guess, that iron in +1 is more towards left side compared to the iron in +2. We can still compare. That won't be the necessary that we can't compare, but then you cannot just give a judgment. Right now, if I'll see two metals, iron and iron, both in same oxidation state, but the spin value is different. Just looking at the spin value, I can say which one would be in the left side, which one would be in the right side. But in this particular cases, we have to get into the d electrons. We need to find out exactly the d electrons, how they are being paired, or they are unpaired, they are low spin or high spin. Then only we can say, okay, on that comparison, it would be on more negative or it would be on the more positive. So this way only the questions will be asked in the exam case. Here too, it is directly being given as oxidation state or spin state, but there it will come in a complex form. Like I was showing in case of the iron cyanide complex or iron water complex. So up to this, is that clear?
Okay, ma'am, clear.
Okay. So now we will move towards next point. That next factor that we have in hand is we have quadrupole effect. So if you remember earlier for the isomeric shift, what we consider a monopole effect. That means for nucleus, we had two assumptions, if you remember, that nucleus needs to be spherical. That means equal charge distribution. We know that nucleus is made up of protons and neutrons, so that's why I'm talking about charge. Total charge is positive only, so it is equal everywhere. And second, that was radius was constant, right? So when we were having electron density around this S electron density we were talking about, that was around the nucleus. With the nucleus was this is only homogeneous. That means it is equal distribution. That's why it was single pole. But for the quadrupole, what if my nucleus, and this condition happens when I have nucleus spin state, because nucleus spin state is assigned with every nucleus. If it is 0 or if it is half, then only I'll be having a spherical nucleus. That is a condition for my spherical nucleus. What if I have I greater than 1? That means I no longer I have spherical nucleus. Now it is non-spherical nucleus. That means the density or the distribution is not constant. It could be having an elliptical shape or any shape. Now more density would be positive towards goes to the pole side, and therefore the negative surrounding here also will go in this particular direction. And if you will see, it is becoming like a quadrupole. When 4 charges are there, it calls as a quadrupole. So earlier it was only 1 because only the electron density was symmetrically distributed because of the monopole thing. Now if I have a non-spherical nucleus which is not symmetrical everywhere, the charge density would be different. That will create a quadrupole, and that is called a quadrupole effect. Is this clear?
Clear, ma'am.
So we need to remember these conditions in mind when we are talking about that. For quadrupole thing, we need to have I greater than half. For having a non-spherical nucleus, I greater than half is the necessity. So this is a necessary condition. Okay.
Okay, ma'am.
So generally the quadrupole effect is being given by this particular formula. We calculate the quadrupole moment, which has been given by EQ, that's a proton charge. Then we have a charge density into R square, then 3 cos square theta minus 1 and dV. This is the volume element. So if you remember that in case of sphere or non-sphere, we talk about general two terms, that is R and theta. What is the distance and what is the angle? That's why it is being given in this particular way. And if we have a spherical thing, then this value becomes 0, and therefore the quadrupole moment becomes 0 because there is no more quadrupole as all. So this is the mathematical equation that we use for calculating the quadrupole moment in case of when we have a non-spherical. Okay, so when we have a non-spherical Is this clear now? Earlier we saw first effect, that was isomeric shift, when we were talking about the interactions of this coordination ligands and coordinating ligands and the oxidation state. Now we have, if we are considering the nucleus to be non-spherical, that is I greater than half, then we have a quadruple effect. The charge distribution would be having 4 charges, and that will be considerable when we are talking about the electric field gradient, the third factor. So is this clear now?
Clear, ma'am. Understood.
Now we are moving towards the third and last factor, which is electric field gradient. EFG, which is related to the quadrupole splitting. That is delta EQ. So these are the two parameters that we are going to talk about now. So firstly, there are certain conditions to understand. Electric field gradient is something which is having some deviation with respect to the length. So if I have a homogeneous field, homogeneous electric field, electric field is related to the charge separations, right? If I have a homogeneous electric field, this is not going to give me any gradient. Gradient, it has to be inhomogeneous. Somewhere it is more, somewhere it is less. So some difference should be there. So in particular case, if I have conditions, I will, or if I'll say it's the cases, different cases. So the first case that we are taking, we have homogeneous electric field and spherical nucleus. That means I is either 0, 1 by 2. So in this particular case, if I'll draw, here my nucleus is spherical and this is homogeneous. That means it is going, this electric field is going in one direction. It is homogeneous. That means distributed everywhere, constant. So this particular way, we are not going to see any difference in the spectra or pattern difference for any other complex. If my nucleus, for say for example, if I'm comparing two kinds of complexes where iron in same oxidation state and it is having either I value is half, that is spherical, and it is been given the electric field constant. So it is not going to show me any kind of difference based on the quadruple splitting. I am not, so both will be having this kind of spectrum. Maybe the isomeric shift would be same, but both are going to have, maybe one is less, one is more, but I won't be able to see any differentiation because the peak is not splitting into two. If at all the quadruple splitting, that splitting is going to happen, this particular peak will split like this way. So we will see the splitting depending upon if that nucleus is non-spherical as well as there is inhomogeneity of the electric field. How that electric field gets generated, that also we will talk about. But firstly, we see what are the different cases. So in this particular case, it is not going to work. The second case, if we have homogeneous field but non-spherical nucleus, right? That means I is greater than half. So if I have a non-spherical nucleus like this way, and still I am having electric field as homogeneous, here also we are not going to see any difference. Because even if my nucleus is not having similar kind of distribution, but the field is homogeneous, it is not going to have any kind of effect on the nucleus. It would be same for everything. Now, third factor is, if I have both inhomogeneous here, firstly, if I have now inhomogeneous electric field but spherical nucleus, that means I equals to half. So again, my nucleus is spherical and now I am having any kind of variation in the electric field, which is not constant, which is not distributed well. So here it is going like this way, then this way, then this, and then this. Okay, so this is inhomogeneous. Here also it is not going to give me any difference because my nucleus. So one of the two parameters is constant, like it is having either the electric field is homogeneous or my nucleus is spherical. It is not going to give me any difference. Whereas the last and important case where both are inhomogeneous, for example, I have inhomogeneous field and it is non-spherical nucleus. That means I greater than half. So in this particular case, if I will draw, here is my inhomogeneous, that electric field is this one, that nucleus is this one. And now my field is also inhomogeneous. So it is not distributed properly. It is inhomogeneous. There would be a gradient. So this particular case, depending upon the different kind of nucleus, I'm going to see a difference. Some difference in the peaks and splitting would occur. Is this clear? I will explain with example firstly, but these four conditions are clear. For having the electric field gradient, we need to have both the electric field to be homogeneous as well as non-spherical nucleus should be there. So is this clear?
Okay, ma'am, clear.
Okay. Now I will explain you with the kind of example. So we are taking first case, generally when we have, I'm talking with the sample only. Here is the ground state and here is the excited state. Excited state we know 3 by 2 and here it is 1 by 2. Now first case, when we were talking about the spherical and non-spherical nucleus. Here, what do you think I equals to half would be having spherical nucleus or non-spherical? So we said that I equals to 0 or half is spherical and I greater than half is non-spherical.
I equal to 0, comma 1 by 2 is a spherical. I greater than 1 by 2 is non-spherical.
So this one is what?
I equal to 1 by 2 is spherical, ma'am.
Yeah. So this is spherical. So therefore, it is not going to have any effect. Whereas in this particular 3 by 2, it's non-spherical. Right? And if I am giving inhomogeneous field, this is going to be constant only because anyway this is spherical only. But here because of the inhomogeneous field, that would split into plus minus 3 by 2 plus minus half, and this is 1 by 2. Therefore now earlier we were having one transition just from this to this. Now it would be having two transitions here and here. So one peak got split into two peaks. So that's why if earlier the spectra was coming like one peak at any delta value, now it is coming like splitting of this particular peak here. So this is my spectra when I'm having an inhomogeneous field as well as non-spherical radius. So is this clear?
Clear, ma'am. Single peak of isomer shift for spherical.
Yeah.
Spherical, two peak of isomer shift
Not
for
just spherical,
non-spherical.
it is also when it is in homogeneous field. So this case, when we have homogeneous field, there won't be any splitting. Even in the non-spherical also, we saw that there is not going to be any splitting. Here, we have both the cases, spherical also, non-spherical also, but I have given inhomogeneous field. That means there is some redistribution of the electric field. So spherical would remain as such. It was not going to affect anything. But non-spherical, in case of the this inhomogeneous field, it will split into two parts. Plus minus 3 half to above, plus minus 1 by 2 down. And therefore, from ground state to excited state, now there is two levels. One is this one, it will come there, and one is ground to the higher level. So earlier we were seeing only one peak because of the inhomogeneous field. But when there is homogeneous field, we were seeing only one field. When there is inhomogeneous field, we saw one peak splitting into two. So earlier it was one. Earlier we can draw it as a dash form here. So earlier we were having, when inhomogeneous field was there, earlier we were having the peak over here, right? This was my delta. Now when inhomogeneous field was there, this peak got split into two peak, one to the left side, one to the right side. Now if I will take up this delta 1 value, this is delta 2 value. So delta 1 plus delta 2 divided by 2 is nothing but my isomeric field, this value. And the difference between these two peaks, that is called as quadrupole splitting, that is delta Q. In this particular case, delta Q is not zero, it exists. So that one peak got split into two. Now you agree, like if I have one apple and now if I'm cutting it into two halves, and if I'll again join that, that would be one apple. Similarly, if I'll take an average of these two values, it will give me again the same peak value which was happening in one peak. But there, if I have cut the apple into two, there would be some difference between the two things. Now you understand that how I have kept like two peaks there, and that distance or the difference between them is called quadruple splitting.
Okay, ma'am, clear. I understood.
Now, the main question that we got, firstly, we need to have, we said that we need to have electric field gradient, and for this, inhomogeneous field is required. So how this electric field gradient, it has to be non-zero for delta EQ to be non-zero. That means if you want a quadrupole splitting, that splitting that we saw, if you want that, this parameter has to be non-zero. That means it should exist. But on what factors it actually depends upon? How do we get to know whether there is an inhomogeneous electric field or not? So this comes firstly from the lattice contribution. Don't worry about the terms. I will explain them with the examples. And second is valence contribution. So lattice contribution says that, for example, something coming from the lattice. Lattice is the surrounding. Say, for example, if I have iron and all the ligands are same. So when there is same, that will give you a spherical kind of distribution, or the distribution is same, right? When everything is same, it is not going to give me any deviation. For electric field gradient to happen, there should be some inhomogeneity. It should not be same. There should be some difference. So if it is anywhere, if it is same, that there won't be any lattice contribution. So this factor is gone. Similarly, valence contribution comes from the distribution of the electrons in d orbital. Say, for example, if I have D6 and D6 is been distributed like this way, pairing has happened, one on the other, the distribution is symmetrical. This is symmetrical, right? Distribution is symmetrical. There is no unsymmetry. Unsymmetry we call it, like, for example, if I have 1, 2, just this D2, that is called as unsymmetrical because the down one, the T2G, is not properly filled. One orbital is empty. Here, all the orbitals are filled and they are filled with equal number of electrons. So, for example, here, if they are filled like this way, the D5, then also it is called as unsymmetrical because one orbital is having only one electron, other two are having two electrons. So that unsymmetry is there. Whenever there is unsymmetry, that will be having a valence contribution. Is this clear?
Clear, ma'am.
So for electric field gradient to be there, for quadrupole splitting should be happening, we need to have lattice contribution, we need to have valence contribution. Even if any of these two parameters is also there, that time also we would see splitting. If both the parameters are there, then the splitting would be very strong. If one parameter is there, splitting would be weak. And if both the parameters are not there, then there is no splitting. Okay, we will see in this case now. Next one. So I'm going to take one example. These points will be clear. For example, we are taking, like I said, I'm taking iron, water molecule 6 and 2. Right? So we are taking iron, water 2.